Hi, good day everyone. Today we will discuss sound and hearing. So sound wave is the most important of all the mechanical waves that occurs in our everyday lives. In this lecture video, we will discuss the relationship between displacements, pressure fluctuation, and intensity of a sound wave. Also, we have the speed of sound waves in different medium. We also have the standing waves and normal modes, resonance, beats, and the last one is the Doppler effect. Okay, sound wave consists of longitudinal waves in a medium. We have to take note that sound wave cannot travel without a medium, unlike electromagnetic waves like light, for example. So imagine if sound wave can travel without a medium, say in space. If sound wave can travel in space, then we can actually hear the sound of planets. We can actually hear the sound of our sun, the crying of our sun, and so on. So imagine if sound wave can travel in space, then it will be very noisy. Okay, we can hear the sun, the sound of the sun, the sound of the planets, and so on. So we have to take note. We have to take note that sound waves cannot travel without a medium, and the medium that we're talking about here are the solids, liquids, and gas. Okay, so sound wave can travel through a solid, through a liquid, and through a gas. Okay, so we also have this uh, range of frequencies that a human can hear. We call this one as audible range. So we can actually hear a sound from this range of frequencies from 20 hertz to 20,000 hertz. Okay, above 20,000 hertz, we cannot hear that sound. We call that one as ultrasonic. And below 20 hertz, we also cannot hear that sound, and that is called infrasonic. Okay, there are animals that can hear um, ultrasonic sound like cats, dogs, and bats. Uh, there are sounds that they can hear, but we cannot hear it because our range of frequencies, our audible range is between 20 hertz up to 20,000 hertz only. Okay, so for infrasonic, elephant can hear some infrasonic sound, and bats can hear some ultrasonic sound. Okay, okay, now we will describe mathematically a sound wave. We have to take note from a previous topic, the mechanical waves. A wave can be described by a wave function. So sound wave can also be described by a wave function. It is denoted by y as a function of position x and time t. And if the wave is sinusoidal, then the wave function can be expressed mathematically into this equation, where a is the amplitude, k is the wave number, omega is the angular frequency, and time is t is time. Okay, so we can actually describe a sound wave by this equation, and we call this one as wave function. Also, we can describe sound wave as pressure fluctuations. And in normal atmospheric pressure, the pressure fluctuation can be expressed into this equation. P, where P is pressure, is equal to BKA sine kx minus omega t, where P is the pressure fluctuation, P is some constant, and that constant is called bulk modulus, and K is the wave number, A is the amplitude, omega is the angular frequency. Where BKA, this one, the product of the bulk modulus, the wave number, and the amplitude, is we call this one as the maximum pressure fluctuation, or sometimes we call this one as pressure amplitude. Okay, so again, we can describe sound wave in terms of wave function, and we can also describe sound wave in terms of pressure fluctuation. And the equations are these. We have y equals this one, where the maximum displacement is a, and the pressure fluctuation is given by this, where the maximum amplitude is equal to bka. Okay, we also have this perception of sound waves. So first is we have loudness. Loudness refers to a listener's subjective perception of a sound sensation, and loudness is dependent on intensity and frequency of a sound wave. So for example, for a given frequency, the greater the pressure amplitude of a sinusoidal sound wave, the greater the perceived loudness. So it depends upon the frequency and the intensity of a sound wave. Also, we have musical tones differ from one another in three ways. We have this pitch, intensity, and quality. Quality, or we call this one as timbre. So what is pitch? It refers to the characteristic of a sound that enables one to classify a note as a high note or a low note. So the higher the frequency take note of a sound, the higher the pitch that a listener will perceive. So we have this high pitch or low pitch. It depends on the frequency of the sound. Okay. Number two is we have intensity. It is measured by the energy of the sound. So later we will discuss, or we will quantify this intensity of a sound. So it is basically based from the energy that is carried by a sound wave. So that's intensity. And for the last one is we have timbre or quality. It is determined in part by the number of overtones present and their corresponding intensity distributions. We also have this noise. Unlike the tones made by musical instruments or the vowels in human speech, noise is a combination of all frequencies, not just frequencies that are integer multiples of a fundamental frequency. An extreme case is the so-called white noise, which contains equal amounts of all frequencies across the audible range. Now let's go to the speed of sound waves. You have to take note that the speed of sound is dependent on the medium used in the system. So for example, in liquid, if sound waves is traveling through a liquid, then the speed of sound is equal to the square root of B over rho, where B is the bulk modulus, which is a constant, and rho is the density of the material. For solid, we have this equation square root of y, where y is the Young's modulus, over the rho, or the density of the material. But for gas, the speed of sound is dependent on the temperature of the gas. So it is equal to square root of gamma RT over M, where gamma is the adiabatic index, which is constant. Say for example, in air, the gamma or the adiabatic index for air is equal to 1.40. R is the molar gas constant, and M is the molar mass of the gas, and temperature T is the temperature, which is measured in Kelvin. So we have to take note that you have to convert temperature into Kelvin. So this is now the speed of the sound waves in gas. Now we have sound intensity. As I said, intensity is measured by the energy of the sound. We know that wave carries energy, and the useful way to describe this energy carried by the waves is through intensity. So intensity is denoted by I, and it is the time average rate at which energy is transported per unit area across a surface perpendicular to the direction of propagation. So basically, intensity I is just equal to the average power per unit area. We have to take note that the average power is just equal to this time average rate of energy. So intensity, it can be written as the product of pressure and velocity. Rewriting this one, in terms of pressure fluctuation and the velocity, we have this. And from that, to get the average of that one, we can express I in terms of this, which is equal to 1/2 V omega Ka squared. So now, from this one, noting that K is equal to omega over V, and V is equal to this square root of bulk modulus over rho, then we can express I in terms of this one. We have P max over 2 square root of rho times the bulk modulus. Take note, P max is equal to the product of the bulk modulus times k times the amplitude A. Okay, so that this is the expression for sound intensity. So for pressure amplitude equal to 30 pascals, the sound intensity would be 1.0707 times 10 to the minus 4. By the way, the unit of intensity is watt per meter square or per centimeter square. So because intensity is defined as the power per unit area, so power, the unit of power is watt, and the unit of area is meter square or centimeter square. So for pressure equal to 3 times 10 to the minus 5, and the sound intensity would be equal to 1.07 times 10 to the minus 16. Also, we can express sound intensity in terms of distance. So we have this variation of intensity with distance. So suppose we have this, if a sound source, okay, this is the sound source here at point P. If a sound source can be considered as a point, then the intensity at a distance r, so at a distance r, so at this point here, the intensity at a distance r from the source is inversely proportional to r squared. So your intensity, take note by definition, intensity is equal to power P over the area, which in this case, the area that we will consider is the surface area of a sphere. And for a sphere, the surface area is equal to 4 pi r squared. And notice, intensity is inversely proportional to the r squared, okay, to the square of the distance from the source, distance r from the source. So if P is the power output, okay, then the average intensity is given by this. So take note, I is inversely proportional to r squared, where P is the power output from the source, or yes, from the source. Okay, so as you increase the r, take note, as you increase the r, the intensity will decrease. Okay, the energy twice as far from the source is spread over 4 times the area, hence 1/4 the intensity. So again, as you increase the r, okay, as you increase the r, the intensity will be reduced, and the intensity obeys the inverse square law. Okay, so we have this I1 over I2 is equal to R2 square over R1 square. Because the ear is sensitive over a broad range of intensities, a logarithmic intensity scale is usually used. So we have this decibel scale. The sound intensity level, beta, denoted by beta, is equal to this one, 10 decibel times the log of I over I naught, where I is the intensity and I naught is called a reference intensity, chosen to be equal to 10 to the minus 12 watts per meter square. Approximately the threshold of human hearing at 1000 hertz. So at 1000 hertz frequency, the intensity is equal to this, I naught equal to 10 to the minus 12 watts per meter square. Okay, so if we rearrange this one, if we solve for I here, solving for I is just equal to this, I naught, which is 10 to the minus 12, times 10 raised to the power of beta, the decibel, the sound intensity level beta, over 10. So we can actually convert I into beta. Also, we can also convert beta into I, which is given by these equations. We can also have this, the difference between 2 decibel sound intensity level beta, beta 2 minus beta 1 is equal to, in terms of intensity 2 and intensity 1, in terms of the distance R1, R2, we have the difference between these 2 decibel scale, and in terms of pressure, we have this equation here. So how loud is too loud? We have this in decibel scale. So we have, for threshold of hearing, it is equal to 0 decibel. It means that the intensity at that point is equal to 10 to the minus 12 watts per meter square. So for sound of whisper, we have 10 decibel, 10 around 10 to 20. We have quite rural setting around 30 decibel, Quiet living room 40 decibels. Normal conversation is around 60 decibels. Passenger car 70 up to 130. The threshold of pain is around 130 decibel. For guitar, rock band around 110. Jet planes or airplanes, it is around 120 decibel. Again, you can convert this 120 decibel into intensities, and at the same time you can convert intensity I into beta using these equations here. Okay, so that's for decibel scale.